Okay, so yesterday we talked about limiting reactants. You had some practice problems to work. You should have finished those up and checked your answers. And what this video was on is just a review over limiting reactants. So I'm going to spend a couple of days working problems. That way everybody really understands what we're doing and then give you plenty of practice before we have a quiz on this on Friday. So I give us about 3 days working these problems. That should be plenty, because we're not doing anything new. We're doing, it's just 3-step stoichiometry problems. But to kind of review, linear reactance is the reactant. It is, I should have said it is the one that is used up in a chemical reaction. It runs out first in a chemical reaction. The excess reactant is the one that is left over. That means you're going to have too much of it. The limiting reactant, once it runs out, when these things are reacting, these two chemicals, when all of that reactant runs out, the reaction stops. So how many ever grams of your products, how many ever grams of those will stop being produced once that limiting reactant runs out. So that limiting reactant determines how much product is produced. The excess reactant doesn't determine it because you have too much of it. You're going to have excess reactant left over. So it's the one that is left over in a chemical reaction, and it'll be mixed in with your product, and you would have to, if you're in the lab, you'd have to separate it from your product. Because, if we have this reaction right here, C2H4 reacting with oxygen gas, producing CO2 and H2O, if we just, I'm not going to put any numbers in here, but let's just say that C2H4 was my limiting reactant, whatever amount I had. When that reactant runs out, the grams of CO2 and grams of H2 produced would be set. That'd be all that could be produced. The amount of O2 wouldn't matter. It's my excess reactant. It wouldn't matter in this reaction because I would have too much of it. So the limiting reaction is the one that determines how much product is being produced. And in these problems, the only difference they are than what we've been working is, in the beginning, the problems we worked, it was like, if I have 10 grams of C2H4, how many grams of CO2 can be produced? And it was just a 3-step stoichiometry problem. Well, now you have, it's telling you the problem, it's giving you the amount of both reactants. Say if you had 20 grams of O2, and it's asking you how many grams of one of your product can be produced and which one's the limiting reactant. So you have to work this problem twice. Once you have to go, 10 grams of this stuff and go 2 grams of CO2. You have to work it again with 20 grams of O2 and go to grams of CO2 and then compare. So what I'm going to do is on this worksheet, you should have this worksheet, limiting reactant worksheet number 1. I'm going to work number 1 with you and then let you work the other problems. All right? So, but right before we do that, I want to review over 3-step grams to grams stoichiometry problems. All right? Let's say that I was given, this, I got my balanced equation. Those numbers, that'd be a 1 there, let's assume, are in moles. I can only use those numbers to go from moles of something to moles of something else. All right? But let's say I had 10 grams of sodium, and I wanted to know how many grams of NaCl could be produced from that. I cannot, in one step, go from grams of sodium to grams of NaCl. Right? To go from grams of sodium to grams of NaCl, I got to use these coefficients, and they are in moles. So I have to be in moles to begin with. So my first step, it's kind of like there's no way I can go directly in one step from here to there. I can't do it. I have to take a detour. First, my first step down through here, I have to divide by the molar mass, and that would give me moles of Na. My next step would be to go from moles of Na to I want to get over here, I want to get to moles of NaCl. That's when I would use my balanced equation. are my coefficients to use. That's when I set up a proportion. I showed you a few different ways to work those problems. Once I'm in moles of NaCl, one more step. I multiply by the molar mass of NaCl, and that would give me my grams of NaCl. So it's a three-step problem. Steps 1 right here is what we, and step 3 right here is what we learned in the last unit. This is nothing new. The only new thing is step 2 right here that we've learned in this unit. So the only thing of problem students have with this is just working three-step problems, just working problems that are long. They know how to do all the steps, but put them all together they have problems with. That's why I said somebody can write on the board the 3 steps for grams stoichiometry. That way you could always look at it and have it to go by. I don't mind if you do that. So now, like I said, I'm going to look at number 1 on your worksheet. I'm going to work it, and then you can work the other ones. So here's number 1 right here. I have it where I can have more room. It says, consider the reaction I2O5 plus 5CO. And remember those parentheses, it says G, which is just telling you the state of matter of that, it's telling you it's a gas. But plus 5 times CO, carbon monoxide, produces 5 CO2 plus 1 I2. All right, and it's telling me if I have 80 grams of iodine 5 oxide, which is I2O5, reacting with 28 grams of carbon monoxide of CO. I want to determine the mass in grams. All it's asking is find the grams of I2, that's iodine, or I2. It's I2 because it's diatomic, it's a molecule. It can't exist, it's just one atom. It's a diatomic molecule. And what is the limiting reactant? All right, so what I do is I'm going to take first my 80 grams of, I'm going to work the problem first for 80 grams of I2O5. And I'm going to do the 3-step stoichiometry problem, and I want to go to grams of I2 that's produced. So my first step is to simply convert to moles. So I take 80.0 grams of I2O5. Now you'll have to add up the molar mass of I2O5. I've already done that, and it is 333.81. And I'm going to divide to get my so that would be 80 divided by 333.81. That gives me 0.24. I can round these to 2 decimal places, so that'll be 0.24. And now I'm in moles of I2O5. My next step, now that I'm in moles, I want to go to from moles of I2O5 to moles of I2. I use my coefficients. The coefficient in front of I2O5 would be just a 1. So that'd be 1 over the moles, actual number of moles I do have. 1 over 0.24 equals, the coefficient in front of I2 is also a 1 because there's not a coefficient there, so it would be a 1, and that's over X. Now I'm looking for X, which will give me moles of I2 that's produced. So when I cross multiply, I get 1X equals 0.24. Divide both sides by 1. X is 0.24. Now I'm in moles of I2, my product. My last step. Now that I'm in moles, I can simply convert to grams. I'm going to take 0.24, my number of moles, multiply it by my molar mass of I2. I've already found that. You just take the atomic mass of iodine, multiply it by 2, and it would give you, I think this is right anyway. If I get these molar masses wrong, I apologize. 253.84 or something very close to that. If it's a few tenths off, then we'll be fine. So I multiply 0.24 times 253.84. That gives me to 2 decimal places 60.92. And that would be grams of I2 that's produced. So if I had 80 grams of I-205, I would get 60.92 grams of I2. Now we have to work the problem again. This time we have 28 grams of carbon monoxide. So I'm going to start another page, and now I'm going to work the problem with my other reactant. 28.0 grams of CO, it's carbon monoxide. My first step, simply convert to moles. 28.0 grams divided by the molar mass of CO. I've already found that. It is 28.01. So I take 28 divided by 28.01, and I get 0.9996, whatever that will round to 1.0, and that will be moles of CO. My next step, I want to go from moles of CO to moles of I2 using my balanced equation. I look for what's the coefficient for a CO? It's a 5, so I'll put 5 over 1.0 equals the coefficient in front of I2 is a 1 in the balanced reaction, so that'd be 1 over X. I cross multiply and I get 5X equals 1.0. Divide both sides by 5, and your X is going to equal 0.2. And now I just went from moles of CO to moles of I2. My last step is convert to grams. 0.2 moles of I2 multiplied by the molar mass of I2. I've already calculated that. It's 253.84. And I get 50.77 grams. And that is grams of I2. So when I used CO, that reactant, I got 50.77 grams of I2. When I used I205, I got 60.92. So I used I205 as a reactant. I got, again, 60.92 grams of I2. So what's the correct answer? Well, we said when limited reactant runs out, the lowest amount is going to be the amount of product that's actually produced. So the correct answer between the lower amounts, 50.77, that would be the correct amount of I2 produced. My limiting reactant would be the reactant that produced that amount. So my limiting reactant is CO, carbon monoxide. The other reactant would be my excess reactant. That would be I205, excess reactant. This amount right here would never be produced because the limiting reactant would run out before that amount could be produced. Okay, so, that's the way these problems will work. There's really, I could work 20 of them, and take up a lot of time, but, they're all worked the exact same way. There's nothing new. What we've covered, this is exactly what we've been doing for 2 weeks now. You're just having to do for both reactants and compare your final answers. Your correct one will be the lower amounts. Whatever reactant produces that will be your limiting reactant. All right, so your assignment now is to finish this worksheet. And again, don't forget our quiz on Friday.